So this is going to be our last discussion on particle-laden flows. Next week we'll start talking about interfacial flows. What we're going to do today is kind of bring everything we've discussed about so far, and we're going to, I'll try to show you that this entire package of methods, well, more specifically, we'll be talking about the Euler-Lagrange stuff, but I'll try to convince you that this package of tools is very much an appropriate predictive tool that can be used to do some interesting science. Okay, so we're not going to focus too much on engineering questions, but we will touch upon a few engineering problems. I've introduced a few examples of a few engineering problems, but instead we'll try to focus on well, at least the focus will be a bit more on the science that we can do with the type of mesoscale Euler-Lagrange tools that we've talked about. So we'll take our equations from yesterday. We'll take our collision model from yesterday. We'll take all those things. We'll put all this together in a flow solver that looks a lot like the flow solver you've played with during the week. Except it's 3D, it's going to be parallelized, and we're going to scale things up and look at the interesting flows that are accessible with this. So it is not going to be like a course lecture type thing. It's going to be closer to a research presentation type of thing. Okay. Please interrupt me with questions as much as you want. I'm not really planning to write on anything. So if there are things that we need to explain, that we need to discuss in more details, or things that I missed entirely that I'm assuming you know and you don't, let me know and I'll stop. Another caveat, I think you have some version of those slides, but some version of those slides, not exactly the same version. There's probably an 80% overlap or something like this, but I had to provide to Professor Day this set of notes a little while ago before I really had time to think about what would be appropriate to show you. Okay, so I gave you a package that is not exactly one-to-one corresponds to what I'm going to show you. Okay, so we'll talk about computational modeling, and here I'm going to talk about strongly coupled particle-laden turbulence. So turbulence is going to be one important aspect of what we're going to talk about, and the other thing is this notion of strongly coupled two-phase flows. I'm not going to be too interested in the situation where particles don't influence in any way the surrounding flow, or vice versa. Situations that are purely granular, where like the beds we looked at the end of our little fun time with the code yesterday, they're not that exciting because they're not really truly multi-phase problems. You could get them right, but by getting only the important phase right. So we're not going to look at that. I have a few examples here of dispersed multiphase flows of various levels of importance, depending on your interest. Obviously, if you are interested in cloud physics and weather climate prediction, this is the type of thing that, that would involve two-phase flows. The simple question, how long does it take for a rain cloud to start raining, is something that we don't know how to answer today. Well, we can observe it, but we don't have closed models that tell us, yes, this is our prediction and we get it right every time. There's in fact about an order of magnitude gap, again, an engineering order of magnitude, factor less than 10, but much larger than 1, between when we think, how long we think it takes for a rain cloud to start raining and what we actually observe. So there's various processes that must be taking place in rain clouds that we're not yet accounting for appropriately, and that involves little rain droplets colliding with one another, growing in their size, some condensation, all this in an environment that's turbulent in which preferential concentration is known to exist. So this is fundamentally a two-phase flow turbulent problem where we're not today able to fully grasp what's going on. This is a picture from, you probably heard and remember back in, I think, 2009, was it, or 11, that this Icelandic volcano disrupted the entire flight patterns of all the aircrafts around Europe because of the extensive ash cloud. And if you remember, this volcano had a very complicated name, and so I learned it. So it's Eyjafjallajökull. So there you go. This is a dense particle-laden flow. This is not water droplets. This is ash. But still, the same story happens here. If you want to be able to predict how dense of a cloud an aircraft can fly through, you need to be able to say something about the distribution of particle volume fraction in systems like this. This is true for forest fires. This is true for any type of pollutant dispersion in the atmosphere at pretty high volume fractions. If we switch our focus completely and start thinking about chemical engineering processes, we're going to be looking at transformation reactors like this power station here. This is a biomass gasification station that is operated in, this is a demonstration plant operated in Vermont in the United States. What you can see here in the center inside the building is the big fluidized bed reactor. So in a system like that, you have a vertical column, you have lots of particles, you have biomass particles, you add heat to this, and you let this cook for a while, and you get the gases, the devolatilization gases out of the system. It's a gross oversimplification, but that's kind of what the focus is, what the focus is. So you end up with a system where there's a chaotic and steady three-dimensional flow wherein we have both particles and fluid interacting. And you're interested in making predictions regarding reaction rates. And reaction rates will depend on the local concentrations, and that will depend on the quality of mixing within a reactor like this. You need to be able to make predictions on that regard. It turns out this is extremely difficult to do, and it's been a challenge. We can make predictions on a certain scale and make models from lab scale experiments. And then we can try to use those models for larger scale reactor and making predictions on larger scale reactors. That tends to fail. So the process of scaling up those type of multiphase processes is today probably one of the biggest hurdle in chemical processing in the engineering world of chemical processing. You know how to operate the transformation on a scale, so the unit transformation is something you control. It's a multiphase process that you can predict. As soon as you try to scale it up to several meters height and a meter width, you try to intensify the process. This is where suddenly the mixing changes, the multiphase flow behaves differently, you have different dynamics, and all your models fall apart. You build something like that, it ends up behaving in a way that's completely different from what you had predicted in the first place. Well, it's another environmental example. There's a helicopter here trying to land, and I think this was our initial, the initial image that I showed at the very beginning of the week. If you want to make predictions regarding spray combustion, again, those spray droplets are going to be, assuming you know everything about your spray droplets, you still need to say something about where they are, how densely distributed they are, and that's going to, again, be an interesting disperse multiphase flow problem. So I suggest we zoom in one problem in particular to highlight some of the multi-scale challenges of particle-laden flows. This is the National Energy Technology Laboratory's chemical looping reactor. This is a chemical looping process. This is, we're not chemical engineers, I'm not going to go into details here, but basically there's essentially two reactors connected to one another, one that feeds to the other one that feeds to the first one in a looping fashion. Those are multiphase reactors, heterogeneous reactors in which we have a solid phase and a gas phase. And the solid phase is in the form of a whole lot of catalytic particles distributed around in the system. So we end up with solid, a gas. In one of those systems, it's going up. In the other system, it's going down. And the flow is highly turbulent, chaotic. And we need to be able to say something about the quality of the mixing and something like that. So if you look at the schematics of such a system, well, this, some of you know a lot about this already. you'll have here your two-phase mixture that rises up, and then you're going to separate your phases, get back your particles. And anyway, this is a pretty standard way that a reactor can look like. This would be the riser column of the system. This is 22 meters in height. Okay. The piece of interest here is that down here, we have lots of particles piled up, accumulated in a fairly dense bed that's bubbling and dynamically moving around. Up here, we see particles being pneumatically transported up in this riser, in this column. If you put a camera right here, which is something that, and apologies, all the labels come from different slides from which this was taken, so don't mind this. If you go all the way up to a region here and start zooming in, you can ask yourself, all right, what does the flow look like? Well, this is what the flow looks like. The flow here, so this is a simple camera that's been, well, not a simple camera, this is a very expensive camera that was put in this flow. This is work by Schaefer and Gopalan at NETL, this energy-focused national lab in the US. All the little white dots here, gray dots, are particles. Okay? You can see them being, first of all, highly non-uniformly distributed in the system. Okay? There's very dense regions, and there's regions completely devoid of particles. This is space filling, right? You're looking at a section of the system made out of transparent material, but the only particles you can see are the ones on the very outer portion of this. You wouldn't be able to see inside because the particles obstruct your vision. So you can see all those clusters raining down the wall. If you zoom in a bit, you can see you can start to see the individual grains. You can see all those particles falling down. This is highly packed. This is nearly close at close packing limits. This is pretty dilute in comparison. You can zoom in further. This is where this study was by Schaefer and Gopalan is very impressive. You zoom in further, and you start to see the dynamics of the individual grains floating around. That's kind of what we were looking at yesterday, right? Those particles are just floating around, bouncing on one another. They're not perfect spheres, but close enough. There's a little bit of polydispersity, but they're behaving kind of the way you would expect. They just are little solids that live their life. Now, so this is what we would, thinking about this problem at that scale is concretely what we're talking about when we're discussing the micro scale, the microscopic representation of this problem. This scale here is getting us to the micron, or maybe a bit more than a micron. The particle here is probably on the order of 100 micron, but the boundary layer at the surface is probably on the order of 10 micron, or we're looking at small processes here. We have particle wakes, we have collisions. This is where the chemical reactions, the heterogeneous chemical reactions in our reactor are taking place. If you were looking at a different system, you might have phase change. If you had a biomass particle, there would be devolatilization blowing for the surface. At that scale, now we're looking at this mesoscale approach that we've been talking about. We're looking at, here we don't see the individual the boundary layer at the level of the individual particle, but we see the collective dynamics and the naturally emerging dynamics of the ensemble of grains. Those length scales extend over a pretty wide range, in fact, all the way up to the width of the reactor, but these dense regions here organize on the scale of at least 10 particles, 100 particle diameters, something like this. This is the scale that will most directly influence the flow field. This is on that scale that we have those dense chunks of particles falling and pushing the fluid out of the way. This is where most of the feedback into the fluid phase will take place. And then if you go back to that scale, well, this is ultimately the scale that typically your chemical engineer will be interested in figuring out. This is what we need to solve. The big challenge we're facing is that what's going on at that scale ultimately will end up controlling what's going on this full reactor. So this is fundamentally a multi-scale problem, and this is something that, that will represent the challenge. Okay, so we'll organize our discussion today into 3 parts. First, I'll go back to the tool aspect. That's fundamentally what I am. I'm a numericist first and foremost. So this tends to be my main interest. So we'll reintroduce or basically package the entire set of equations we talked about yesterday into a computational flow solver. And then I'll try to convince you that this has pretty darn good predictive capabilities for non-trivial particle-laden flows. So we'll do we'll do a little bit of verification, and then we'll do quite a bit of validation against experiments. Then in the second part, we will take a step back, move away from the comparisons against experiments, and we'll ask ourselves, now that we have this tool, can we maybe create a perfect toy problem? Well, perfect is a big word, but an interesting toy problem, a reference problem that encompasses a lot of those physics. So we'll do that. We'll create a case that will allow us to identify really some of the fundamental dynamics here. So in the same way that, that we discussed preferential concentration a little while ago, and in doing so, we introduced the concept of this Maxey theory in which particles are ejected out of vortices, accumulate in regions of high straining. Well, we'll kind of do the same thing, but now not looking at turbulence leading to preferential concentration, but instead looking at naturally emerging clusters. So we'll provide a more mechanistic explanation for why those clusters emerge. And then we'll conclude with well, I guess more of a double-part discussion about, well, how would you go about doing rents with this? How would you go about building a model that's not unreasonably expensive? Okay, so we'll take a few steps in that direction. This is getting quite a bit further away from my expertise. So this is, in fact, this will be a lot of collaborative work with Rodney Fox at Iowa State University. And then, because I'm more of a big calculation type of person, we'll kind of zoom back into a slightly different version of that problem to help us understand again, if we were to build a proper rents model, what type of property would it have to have in order to get some of the right physics? Okay, so that's kind of the overall plan for today. So we'll start with those predictive simulation capabilities. Okay, so this is kind of the overall recipe. We have a continuous gas phase, a dispersed solid phase. Our particles are not tracers. They have finite inertia. We are going to be facing head-on particle-particle collision. We do not want to shy away from significant mass loading. The mass contained in the particle phase will never be, we expect it to potentially be very significant. We expect things to be non-trivial at the particle scales in the fluid phase as well. And we're going to be specifically interested in situations where there's going to be sustained slip between the phases. Okay, and in particular, gravity tends to help us do that. If you let particles fall under gravity, they tend to slip with respect to the surrounding gas. So we've discussed already that probably the most natural, the simplest, most obvious way that one can try to tackle this problem is by simply going after the micro scale, because at the micro scale, all the relevant physics are known, assuming that there's nothing, that there's no complex chemistry at the surface and that we have spheres. Everything is essentially known. So we have density momentum equations for the fluid phase, we have a boundary condition, and for the dispersed phase, we can write Newton's second law, linear and angular version of it, and we can write our collision force from some smart person who knows about contact mechanics, and we should be all set. It's all fine and good until you go back to a little bit of a back of the envelope calculation, seeing how far you can take such an approach. So thinking again about this typical chemical engineering problem, if I give myself a vertical column in which I have particles rising due to pneumatic transport by a fluid flow, even at the laboratory scale, even a small, little tiny reactor that's not even a meter high if you assume that you have particles that are 100 micron in a tube that is, say, 5 centimeters in width, then we've argued using an immerse boundary type of strategy, it's reasonable to expect that you need at least 10 points per diameter. You probably need more than that. But if you put 10 points per diameter, assume that the particles are essentially going to be space filling. They're going to be occupying pretty much every single region. There's no real opportunity for locally refining the mesh. So you're going to end up requiring essentially on the order of 10 to the 12 grid points to capture this reactor. My code scales pretty well with 1/10 of a million points per core. We can take that to, as long as you can, as you have enough memory to distribute your problem such that there's about 1/10 of a million cell on each compute core, we can scale up to hundreds of thousands of compute cores with pretty good efficiency. But still, if you assume perfect efficiency, you would still require on the order of 10 to the 7 compute cores. That's an enormous amount. It's not necessarily something that is completely out of reach, but to give you a reference, Titan is no longer it's in fact now pretty far from the largest supercomputer, but that was just a very few years ago. One of the most straightforward leadership scale computing facility that was available to individual researchers in the United States by just writing proposals. You could just get access to Titan. It was a highly competitive process, and you could run jobs on this national lab resource. That's this number of cores that we talked about, that would represent about 17 times that national resource. So this is not something you would do every day. This is not something you would do at all on Titan. Even running on 1/10 of Titan would be an enormously expensive and difficult simulation to organize, to put together, just freeing up enough of the machine. If you're a company, you probably don't even want to think about doing even a millionth of that. So we're orders of magnitude away from being able to tackle this problem this way. We need something else. This is where we introduced our mesoscale volume filtering strategy. We're going to explicitly give up anything that has to do with the micro-scale process, because we're going to claim that this is something we can model fairly efficiently. So we'll reformulate our equations such that we don't need to mesh down to a scale below the particle scale. We're going to do that by introducing our filter kernel G with a characteristic with delta F. So that's one way to think about it. We're going to take the particle scale information and spread it out to a surrounding region to make it resolvable on a coarser mesh. In the process, we have a definition for our local volume fraction, and we can define any filtered variable any way we want. Of course, if we're filtering quantities, we have enclosed terms that show up. We shouldn't forget about that. So the approach turns out to be pretty flexible. It's not decoupled from what a lot of other things that have been tried. So in fact, if you let this filter go down to a very small scale, smaller than the particle, which kind of defeats the purpose of what we're trying to do. But if you do that, you kind of go back to this pretty standard immerse boundary schemes that are out there. Okay, that's one way. If the filter is small enough and the limit is small filter, you're now resolving again the flow all around the particle. If, however, the filter, if it is much, much larger than the particle, then we're kind of going back to the pretty standard point particle Lagrangian methods that have been used for a good number of years as well. So we're trying to explore what's going on somewhere in the middle here, where our flow resolution is about on par with the scale of the particle. We're trying to get to a point where we're hoping that we can bring our mesh resolution close to the particle scale, not below the particle scale, but close enough that we can explicitly capture the clustering phenomenon on our grid without having to model it, without having to re-inject it in the form of modeling assumptions. So I included this paper in your course pack, I think in yesterday's afternoon session. This is where this is all laid out, and we discussed about some of that yesterday. So we're not going to go through this, but we derived a good fraction of those terms yesterday. This is the resulting set of equations that you have by simply explicitly applying this filter. This is how this looks. And now this method will echo in a way the multi-scale video that we saw before from Schaefer and Gopalin. We'll have the micro-scale process in which we have lots of spheres bouncing off one another. This we will model. While the collisions will explicitly account for, but the momentum exchange between the phases we will model. So this is that micro-scale. This is not fully captured. This is partially modeled. But those dense regions here, those clusters, you can see the underlying mesh, they will be fully captured explicitly. So we don't need to say anything regarding the physics of those clusters. They will be directly, naturally emerging and fully captured on our set of equations. And then provided we have enough computational resources, we can scale up our mesh to the point where we have many of those clusters interacting with one another, and provided the problem is not too large. So again, we're going to have to shy away from real engineering applications, but if the problem is not too high in scale, we can get all the way up to a reactor scale, at least the lab scale and reactor scale. So we wrote the equations already, so I'm not going to say anything more on this. We're going to use a soft sphere collision model for, I think, almost everything I'm going to show you. We talked about how we're going to do the momentum exchange. I mentioned briefly that there's this Trinity and Subramanian correlation as a function of particle volume fraction and Reynolds number that we're going to rely on in order to model what's going on down there. One more little sidestep in the discussion of the numerics. Let me make sure that the time. So one more comment on this. So those are some of the tools that are required to make this work. Let's talk about some of the things we've talked about already. The momentum exchange we detailed already yesterday, so I'm not going to say anything more on this. Soft sphere collisions, we talked pretty extensively about that yesterday afternoon, so you know how this works. So that's part of the story. There's one thing that we didn't talk about, which is how do you deal with collisions in a scalable way if you have multiple processors. So if I have a subgroup of my particles lying on processor A and a subgroup of my particles lying on processor B, how do I get a particle from group A to collide with a particle from group B? Well, that kind of sucks. There's no alternative to that. You have to communicate and exchange your data. So you need to create safety regions in which you go reach out to the other processor, gather particles, bring them to your own processor, and collide with them, and then return them. So that increases the expense, but it's completely doable. Ultimately, we've introduced a filtering technique, so we need to think about how we apply this filter. Well, everything we've discussed about sounds a lot like explicit filtering of Navier-Stokes, and that really is what it is. So it's like an explicit filtering or an explicit LES type of approach, or the simulation type of approach. Well, if your mesh size is on par with the filter size, then you can kind of forgo this step and simply rely on implicit filtering. So you'll rely on the mesh to make sure that you don't generate flow features on the scale below the scales that you're interested in modeling. As far as the particles are concerned, you still need to apply this explicit filter because the particles will carry information on their own scale, which is independent from the mesh. And so for that, we'll have to make use of our filter. How does it work? Well, this is an interesting concept. Now we're saying that each particle should be able to influence a region around itself of a characteristic scale that is set by this filter size, delta F. And we argue that delta F needs to be much larger than the particle size. Well, that means that each particle will have to influence a pretty significant number of grid cells around itself. If you want to do directly, so remember, the way we implemented things in the past few days is each of our particles was allowed to only influence its own cell, the cell in which it was living. It was very cheap. It was also pretty naive. This approach here requires particles to be able to influence an entire region around themselves. But if you imagine you're sitting at the location of one particle, you need to send back information to the fluid in, say, 100 cells around yourself. It's going to be expensive. So you need smarter approaches than just directly reaching out to cells. What you can do is do something similar to what we've done this week. Send your data locally to your closest cells, and then apply a diffusion operator that you can implement implicitly that will directly give you an equivalent filter. So a simple diffusion of a sharp Gaussian will give you wider Gaussian. If you discretize a diffusion operator, apply it on a very sharply, on a very sharp Gaussian kernel of influence for your particle, you can spread it out to many cells at a low cost. So that's what we're doing. You have to do that in a way that's conservative. But then what you can show is that with this approach, obviously, now the parameters, the filter size. If you refine your mesh, you should see convergence. And that's exactly what we're showing here. We can get nice, clean convergence as we refine the mesh size, even if the mesh size is much less than the particle size. We've basically explicitly given up on any information that exists on the scale below our filter scale. Okay. I've hidden a few things still. And I think we discussed that topic briefly yesterday. If you just take this and try it out, probably the simplest case you can look at is let one particle fall under gravity, low Reynolds number. You just let it settle under gravity in a static fluid. It's very easy to solve for the solution to this. The analytical solution would be an exponential rise to the velocity that is exactly what I wrote u here, which is the settling velocity of the particle, which ends up being just tau p times g, the gravitational acceleration. Okay? So this is just a direct analytical solving. This is a linear problem. It's easy. This is what we expect. Well, if we take our code and run this problem, this is what we see instead. It looks right, but it misses the mark by about 10%. We can't even predict the right free-fall velocity of a particle. Why is that? Well, the reason for that is that we've deployed this entire tool in order to allow ourselves to refine our mesh to a point where we're basically resolving our flow on the scale that's close to the particle, not below the particle scale, but close to the particle scale. So what we've observed, and other people have observed as well, is that, well, the particle, because it is two-way coupled, as it falls, it will influence and modify the surrounding flow field. Essentially, it will establish a wake around itself. And that wake will be supported on the mesh. At least part of it will be seen directly by your flow solver on the mesh. The issue is that your drag law requires you to provide local velocity information. Your drag law requires, in everything we wrote, we asked for the flow velocity at the location of the particle. But really, the flow velocity at the location of the particle is heavily disturbed by the presence of the particle itself. So really, what the drag law, at least the drag laws we've talked about so far, require is the velocity that would be at the particle location if the particle wasn't there. Right? If we were able to conceive a situation where we remove our particle and look at the flow velocity there, then our drag law would do great. Well, unfortunately for us, we don't have easily access to this information. So to try to sketch this, if I have this, I guess I have a circle here. Well, I don't know what's going on. Okay. I don't know exactly what happened, but there's been some weird thing with with a sequence of animations. But anyway, so if I have a particle here, and I guess here right now I'm making it move up, so that's not the most, that doesn't really correspond to the falling situation. But anyway, if I have a particle at that, why is the particle not showing? Well, anyway, imagine I have a particle at that location moving up. It will drag the fluid with it, okay? And now the issue is that I will need to, when we evaluate my drag, I'll need to say something about my fluid. And here I'll use some notation that says that locally I'll want to use my local fluid that I'm solving for, and I want to interpolate it to the location of the particle. Well, you can see if I were to interpolate between that phase and that phase, for example, I would find that my velocity is very far from 0. And therefore, my drag would be much less than the drag that a particle that's free-falling in static fluid would feel. So it would be useful for me to be able to predict the undisturbed values of velocity as well as volume fraction instead of just my calculated values. So I'll show you some recent little exercise that we've gone through to try to fix this problem. There's a couple of other recent papers that have come out that, that are attempting to address this. What we're doing here is simply recognizing that we know a lot about how the flow field has been modified. In fact, we know everything about how the volume fraction field has been. Remember, the volume fraction itself shows up in the drag calculation, right? The Tennessee and Subramanian correlation, it uses volume fraction information. So our volume fraction also needs to be corrected. Well, as far as volume fraction is concerned, we know everything about how our own particle ended up modifying the field of particle volume fraction. We know that analytically. It was obtained from an explicit filtering process. So we can subtract that. If I assume my filter to be Gaussian, then I can subtract the Gaussian coming from my own particle and get my corrected solution. You do that analytically. Now you are literally interpolating from a field that is unaware of the presence of the particle. Well, now the velocity is more tricky, because the velocity, you don't get it directly. You feed the source term to the Navier-Stokes equation, and the solution of Navier-Stokes in the presence of that source term is what returns the velocity field. So there's an entire mechanism that modifies, that creates a difference between what you feed to the particle phase and what you need to get back from it. So there's no general analytical solution for the fluid velocity given the influence of a particle, or else we wouldn't be talking about all this. But in the limit of low enough Reynolds number, well, in fact, there is, right? We can say that we know exactly that our particle is locally enforcing a Stokes flow around itself. So if, at the very least, my Reynolds number is, say, on the order of unity, I would expect that I can just subtract the Stokes flow induced by my own particle and fully fix this problem. So this is, as far as we went with this, and we tried this out. This was our blue solution here, uncorrected. If you correct it, boom, it goes back to pretty much exactly the expected value. So that seems like this would not be, at least it was easy to ignore this problem, but that ends up being a non-negligible issue. You can gather all this into, we have a fairly recent paper in which we explored the influence of something like that in a range of cases for lots of different Reynolds numbers, Stokes numbers, et cetera, et cetera. And what we saw is that it allows us to typically reduce the error in terminal in terminal velocity. I hope that I'm still going to be able to talk next week. Yes. Yeah. Well, so let me drink something. As far as the volume fraction is concerned, none. It's a purely additive thing. So we can deal with multiple particles. As far as the velocity field is concerned, well, this is more of a problem. So in the limit of low Reynolds number, the equations we're solving are linear, and so it is still an additive problem. So if we make the assumption that the Reynolds number is fairly low, we are still free to deal with single particles at a time. And that's as far as we've gone. If the Reynolds number goes higher, well, you'll see here that a correction ends up giving higher errors, in fact, than if we were doing nothing. So that's not due to multiple particles, but this is already a heads up that, yeah, careful, this is not a solution that's portable to any situations. So there's a recent publication that came out from Stanford, from Annie Manny's group. A student, Jeremy Orwith, who was a Cornell graduate, looked at another approach for doing this, where instead of trying to subtract the local Stokes flow due to the particle, what they said is locally, we essentially can measure some level of curvature in a flow field. And they just said, let us fit this, let us assess this level of curvature and simply subtract that, okay? So it kind of goes back to, it's kind of the opposite to Faxon's model. Instead of trying to account for the existence of curvature and the way it modifies drag, we're going to say, well, any type of local curvature in the flow field probably comes from the fact that the particle has modified the flow field itself. The issue with this is that it's very tunable. So and they didn't really show better performance for high Reynolds numbers, but I think this is also a very interesting idea. That is more pragmatic. Instead of saying, well, I have something analytical that I can say about my flow field, they say, well, I don't know what to say, but probably if my flow field is very locally curved on the scale of the particle, most likely that's my fault, let me remove that. But this, well, so there's different things. There's multiple questions that are contained in there. First of all, is this something we need to correct? Well, in theory, if the wake that we've generated from the first particle that we're trying to remove here, if it is in fact present on our flow solution and pretty accurate, then it is a good thing, because that means that the second particle behind will feel the modified velocity field due to the particle in front of it, and it will have a better estimate of what is the local flow field it's feeling. So the inference from other particles on ourselves is something that is a feature, not a problem. Now you could say, well, first of all, do we trust the accuracy of our wake, right? We've been developing tools that try to remove some of those local microscopic features of those wakes. So why should we trust them? Well, we don't. There's no reason why they should be very accurately captured. So we have some remnant of those wakes. What I'm saying clearly is that if you're particle A, then your own wake shouldn't be something you feel, or else it's a bug. You're misusing the classical tools particularly you're misusing classical drag correlations. But if you're particle B behind particle A, it is a good thing that you would be in fact feeling explicitly from the solution the effect of particle A. Are we doing enough? Are we capturing this effect enough? The answer is no, and we know that. And in fact, there's an interesting series of papers that came out from Balachandra's group at University of Florida. For the past few years, they've been building a model that is calling PIEP, P-I-E-P. It's an acronym. And that model essentially looks at full direct numerical simulation of different particle arrangements. Well, it's not quite as simple as that, but essentially it is what it is. You look at what would be the effect of putting a second particle behind or somewhere, anywhere around a first particle. And you tabulate that, and then you make use of this as an additional contribution to your drag law. What is shown is that if you do that, you end up predicting quite a bit of additional dynamics that would not be captured in the type of models that I've been describing here. And so this is, again, one way that Lagrangian simulations can be very powerful, because they know everything about the multi-particle, at least they have one realization of the multi-particle density function. And so you can say something about yourself knowing something concrete about other particles. And that allows you, therefore, to have multi-point, multi-particles drag closures. A Uline model wouldn't be able to make use of this. But this is a very good question. This is kind of where the community is slowly going. So it is relevant. Yes? Yes. 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 I'm saying nothing about the Kolmogorov scale. We've talked about here the particle scale. The Kolmogorov scale could be less than the particle scale, in which case, by definition of what we're describing here, we would not be capturing it. The Kolmogorov scale would be another magnitude larger than the particle scale, in which case this method might completely resolve the Kolmogorov scale. Say it again? Wait. So nothing in everything I've said has mentioned anything about the ratio of the Kolmogorov length scale to the particle scale. We've only spoken about the assumptions / requirements that we're placing on our tools regarding filter size, cell size, and particle diameter. Now, you could have a situation where your entire range of scales in the turbulent flow is larger, including Kolmogorov scale, being larger than the particle diameter. Right? It's conceivable. Or alternatively, you could have a situation where some of your turbulent length scales are larger, some of your turbulent length scales are smaller. Okay? So if your argument is using a Stokes flow to correct is not going to be always valid, I absolutely agree. It's only valid in the limit where the particle Reynolds number is small. But there's no inherent contradiction that I see, at least, because we haven't said anything about, we haven't limited ourselves to situations where the Kolmogorov scale is smaller. Yes, I absolutely, I agree. I think this specific correction is not the end of the story. This is, as far as I know, they are, I think I'm aware of a total of 3 papers now that have explicitly head-on addressed this question, that really, if you want to properly resolve, if you want to use a fine mesh in a two-way coupled simulation, you better be careful about correcting your drag, or else you're going to get bogus results. This is one of those 3 papers. Okay, this is not the only one. The other one is the one of by Alimani that does that from a more geometric standpoint, but it does that also in the limit of low Reynolds number. And there's another one also in the limit of low Reynolds numbers working at this question, and that's, I can't remember the authors, but they're from Italy. This will be, other people will continue to work on that and will continue to work on that. I think we need to find how to systematically correct those problems at higher Reynolds numbers too. I absolutely agree with this. Other questions? Yes? So those are my equations. I'm sorry, it seems that I haven't been able to converge on whether I should use alpha or epsilon for the volume fraction. This is the fluid volume fraction, fluid density, fluid volume fraction, fluid density. Those are the equations we derived yesterday. Fluid volume fraction, fluid density, filtered fluid velocity, et cetera, et cetera, et cetera. So yes, we are fully accounting for the volume fraction. There's no choice here, really. If you filter your equations consistently, this is what comes out. It's not a decision of whether you should include it or not. This is what the math tells you you should do. Right. So if you know something concrete about, if you have a reason to think that your volume fraction will, your particle volume fraction is always going to be negligible, you can neglect it. All I'm saying is the equations call for this to be present. And it's not, as long as you have a viable density code, there's exactly 0 cost in including it. That's not true. There's a product that needs to be done. So we talked about the velocity correction. We talked about that. OK, so let's look at some pretty pictures. So I have some validation cases, the validations against experiments. Some of them are pretty old. They come from our first attempts with those techniques. And some of them are much more recent. This should look reasonably familiar to you. This is essentially where we finished up yesterday. It was a very slightly agitated bed, except now this 3D. And again, here we're accounting for volume fractions, so it is more appropriately bubbling, while what we had was not fully realistic bubbling. There's two colors here because we're looking at large particles in red and small particles in yellow. We're blowing from the bottom. What we should see here is the so-called reverse Brazil knot effect. The Brazil knot effect is the fact that the Brazil knots, the biggest knots in mixed knot packages, are known to, upon transport and shaking, travel all the way to the top of their container. The reason is that the smaller particles are capable of navigating their way to the bottom, therefore overall minimizing the total potential energy of the system. If now you're flowing from the bottom, you've kind of flipped the direction of potential energy. Now you're looking at a situation where the small particles are traveling through the cracks and should be expected to get to the very top. So this is a reverse Brazil knot effect. And we're saying that indeed it works. So we observe segregation. That segregation, do I have? Yes, I have. Well, I'll show that in a second, but we'll look at comparisons against experiments regarding the evolution of the segregation. This is a spout fluidization problem. And this is both a fluidized bed with a central spout, for which there's experimental data available. This is not 2D, this is pseudo. At least this is a thin 3D calculation. This is a full 3D spouted bed, for which we had experiments as well to compare against. So you can see the central jet of particles slowly making its way. Slowly, it's going to go there. It's going to form a nice bubble and burst, and there you go. This is one of the largest calculations we've done with this type of approach, still in this dense flow regime. This is now a full model of an actual fluidized bed reactor that was operated for a few years while the Department of Energy's Office of Biomass Research was interested in gasification. It lasted for a very short period. The Office of Biomass Research in the US has had different focal directions. It was really focused on gasification of biomass for a while, then started refocusing more on biomass pyrolysis. But for gasification purposes, they were looking at a bed like this. This is a pretty tiny reactor, but that was built. So this is a lab-scale 2-inch reactor. We had the full CAD of the reactor. We had the real distributor plate in the bottom. And so you can see that from the tiny holes in the distributor plate, you can see, oh, I should say what I'm plotting here. I'm plotting isosurfaces of particle volume fraction. Okay, so what you're seeing here is the bubbles forming within the packed bed of particles and rising and traveling through this. This is a cut through that. You can see the bubbles traveling and moving up and bursting at the surface. And this is the gas velocity that you can see traveling through the cracks and essentially traversing the system. All right, we can take a quick look at each of them. As one of the first comparisons we did, the segregation rate is reasonably well predicted. So this is the vertical segregation between the two colored particles, and this is the lateral segregation. The lateral segregation should be non-existent, and it is essentially non-existent. The same, but there's pretty good comparisons against the experiment of Goldschmidt et al. we think the slight departure in the curvature comes from the fact that we assumed that we could take a slice of the 3D bed, while instead in the experiment they had walls compressing this entire thing. So that they had, so we modeled that using only side walls that you can see in gray here. We didn't have walls in the third dimension. So we think that this is the reason why we have this departure, but we would have to revisit that to ensure that this is the case. But overall, still the segregation is clearly about where we want it to be. The spouted bed, we had particle mass fluxes at different locations. Those are two examples that encompass pretty well what's going on. The comparison is pretty decent with the experiments of Link et al. In 2005. But it's also, we didn't pick the best places for comparison. We also wanted to highlight the fact that the walls are not particularly well modeled here. We have some uncertainty regarding probably the characteristic roughness scale and whether our collisions, so right now our collisions with the wall is essentially basic, modeled the same way as particle-particle collisions. It's very likely that there's roughness, that there's different characteristics at the wall that would prevent such a large negative mass flux along the walls. The particles are rising in the middle, falling on the side. Positive mass flux here, higher than 0, negative there. For this NREL 2-inch reactor, well, they shut down the program, unfortunately, before they really started collecting experiments. They had these different pressure ports here all along, and they had this little probe here that they were supposed to move up and down. This, they ended up stopping all this. They built the entire system, and then they shut it down. So we never got any experimental data, unfortunately, for this problem. So we had to go back instead to experimental correlations. There's a good number of experimental correlations for bubbling fluidized bed, and probably the most well-used one looks at the ratio between the bubble size, so the region devoid of particle, divided by the bed width as a function of the height of the bubble centroid. So we developed a bubble tracking algorithm that followed those bubbles, and then we collected statistics on those bubbles. The experimental correlation, I should have provided the reference, but I can look it up if you're interested. The experimental correlation is the black line here, and our results seem to follow pretty well with this, at least in the top part of the bed. At the bottom of the bed, there's no real expectation that we should match general correlation data because our bubbles are fully controlled, as you can see in this movie, by the local characteristics of our distributed plate. So we have this collection of little holes. The bubbles are exactly starting at the size of those little holes. Okay, and the number of them and the way they move is controlled by the way this distributed plate is set up. So from this, we would say that we think that we have a pretty decent validation of this type of approach for dense flows. Yeah, so don't be scared of using Lagrangian methods for dense flows. They work. How about dilute flows? Well, for dilute flows, there's been a lot of Euler-Lagrange work that's been done over the years, an enormous amount. So our main concern here was whether there would be any value in this type of approach, first. And second, well, remember we talked about this assumption of a separation of scale. We basically argued that if we want our Lagrangian phase to give us useful information, we would need to be able to say something on the scale of the interparticle distance. We would want to have several particles inform the fluid of what's going on. If you have isolated particle, this idea of using a filter is, well, nothing more than a standalone region of influence that doesn't necessarily match the physics in an obvious way. So it would be ideal for us to solve our equations truly on a scale that is larger than the interparticle scale, but less than the clustering length scale. But if we have a dilute flow, we don't have clusters anymore, and our interparticle length scales becomes large. So we can't really make this argument anymore. So we were worried about what was going to happen, but we were eager to look at that. So we looked at a set of experiments that have been conducted by John Eaton at Stanford for the past decade or so, or not the past decade, but during the late 90s and early 2000s. He had a number of students. Probably the most well-known is Kulik, who developed a number of experimental results and wrote papers commenting on the influence that particles have on the turbulent channel flow. Okay, so their interest was, if I put particles at different mass loadings, but still low mass loadings, in turbulent channel flows, what is the consequence on my turbulent channel flow? But then after that, they started looking into somewhat even higher volume mass loading. So this phi here is this mass. This is the mass ratio we talked about. I think we called it C before. This is the ratio of the particle mass to the fluid mass. And in those two PhD theses, those are small values, 0.2 and 0.15. But they're not negligibly small. They're getting to the point that they're not that small anymore. So that's a heck of a lot of particles. Those are tough experiments to do. They're turbulent friction velocity based Reynolds number for the channel is an RE tau of about 600. So it's a pretty high Reynolds number, but not enormous. We simulated this using full DNS resolution. So basically, if we were to remove our particles, our mesh would be sufficient to do full DNS at that RE tau of 630. Okay? So we do full DNS of the gas phase, and now we're adding particles to match the Benson data at 15% in mass. Okay? The corresponding volume fraction is very small. It is in fact on the order, it is less than 10 to minus 4. Okay, so this, from what we said before, you might say, well, that probably means that we don't need to worry about collisions. Well, I'll show you first that this works. So we compared our data to the data of Benson. I'll make a little note here that we first compared our data against the data of the experiments of Paris, and we could not get anything to match. And we were really worried for several months until I had a discussion with John Eaton on this, and he said, oh, you're looking at the Paris data. Yeah, we figured out afterwards that after running this channel for a long time, our walls were crazy rough. And so this is not a smooth wall experiment, this is a highly rough wall experiment, just because the accumulation of collisions of the particles with the walls ended up creating a very complex roughness pattern all along the experimental apparatus. So they fixed that. They went to a tougher metal for the wall. They changed regularly their plexiglass for visualization. So anyway, they figured this out, and they recreated an experimental data set with smooth wall afterwards, and so that's what we're using. As soon as we went to this new data set, everything started matching beautifully. So I'll show you three comparisons here between our simulations and the experiments. The lines are going to be coming from our code. The symbols coming from the Benson data. This is the mean velocity profile as a function of the position. This is not shown in the standard way because I want to show the particle as well. So this is not shown in ln log scale in plus units, but this is shown in a pretty naive mean velocity as a function of position type of way. So the velocity matches well with the experiment. For the gas phase, those are the dots and the open symbols, and the full symbol as well as the continuous line. This is the mean streamwise particle velocity. It matches well. In particular, it matches well down to the very near wall behavior where we see a flattening. There's no reason why the streamwise particle velocity should go to 0. The fluid goes to 0, the particle should still allow us to travel along. This is the fluid fluctuation that matches well as well. And finally, to have a sense of whether we capture the fluctuations of the particle velocity well, this is the full PDF of streamwise particle velocity that was measured by Benson in the very near wall region. And this is, or maybe this in the sun. Wait, this is close to, oh, this is, yes. So this is a near wall region. The symbols are the PDF from the Benson data, and this is a PDF from our measurements. So even from the perspective of the full distribution function of velocities, this matches really well. Yes? I can fix my, yes. 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 So this is, so if I understand correctly, you're saying, in terms of looking at non-dimensional groups, let me try to rephrase and you'll tell me if you agree with what I'm saying. It seems to me you're saying that, yes, mass loading is one parameter, but, or let's say volume fraction is one parameter, but L over D, or height of the channel over D, is another parameter. And increasing, so you try to connect the two in what you're saying, and I'm not sure, I see how they are obviously, they control to some extent the geometry of the problem, so they're not unrelated, but you can change your density independently of your, you can change your mass loading independently of that height ratio, right? So is your question just, is the height of the channel to the particle size important? Is that your question? Okay, so for a fixed volume fraction, yes, okay. So now I understand the question. So the answer is it depends, right? This is always the answer. So it depends. In a situation like that, if you were to keep the Reynolds number the same, the mass loading the same, and change this ratio, it would not have a significant influence. And some of the flows I'll show very soon, it will. The question is the flow, so I can't really give you, well, okay, this is an interesting question. I'll tell you what I think the answer is. I don't think this is necessarily a well accepted theory or published theory or anything like that, but really I'll show evidence that the behavior of a flow like this depends entirely on whether the particles are dominating the production of kinetic energy, or whether the fluid and the presence of a mean gradient in the fluid is dominating the production of kinetic energy. In a situation like that, I'm going to say clearly that because of the mass loading, and I'll show evidence for that later, it is entirely the single phase process, the mean gradient production, that controls the flow. This is what leads to the existence of turbulence and the agitation and all this. So provided you kept the Reynolds number the same, you could change this height, nothing would really change. If you were in a situation, however, where the mass loading was sufficiently higher, then the particle dynamics would be the one that would essentially control the entire flow. And then you would end up with a very different story, because this is where you would transition to clustering. And there we observe that cluster sizes, they tend to be very much set by the channel width. It's not, and the reason for that we'll touch upon as well. The fact is that a natural cluster is an enormous thing, a very large object, and you can estimate its size. And that size tends to be much larger than most reactor sizes. So the answer would be that it depends. Provided that this L over D is large, I think it would not have much of an impact provided that the mass loading is fairly low. If the mass loading is high, even for large L over Ds, changing it will change the response of the flow. Let me make one more point on this. Look at this guy here. I mentioned here, no one seemed to be concerned by this. I mentioned that the velocity, the particle velocity profile flattens near the wall, okay? I also mentioned that the volume fraction here was much less than 10 to minus 4. Much less than 10 to minus 4 means we can do without collisions. Of course, we have to account with collisions. We have to account for collisions with the wall. Sure, but interparticle collisions, according to classical understanding of the probability of collisions at such low volume fractions, we don't have to worry about it. Well, we ran our first simulations with this assumption. Let's not put collisions in, right? Why would we need to deal with that expensive aspect? Well, what we found is that our predicted velocity profile ended up going much closer to 0 near the wall. Okay? Much lower velocities were reached. We found something else that will echo some of the comments that I heard earlier this week. This is our number density profile as a function of the position along the channel. Initially, we distribute our particles randomly. They are equiprobably distributed in this space. If you run without collisions, you converge to something like this. There's a somewhat higher probability of finding particles in the middle, less so in this region here. I'm sorry, I'm following the wrong one. No collisions, red. So we have about 50% higher probability compared to the initial, I guess 60% higher probability compared to the initial, or compared to the average number density of finding particles. About a 30% lower probability within essentially the log low region of finding particles. And then we shoot up to a significant pileup of particles against the walls. So no collisions leads to prediction of many particles against the wall. And we don't have experimental data on this, by the way. So we don't know which one is correct. However, we have experimental data on this, and there we can say something about what's correct. So without collisions, we have lots of particles stuck against, well, stuck, not really, they still move, but slowly. Lots of particles against the wall, and overall, the particles are moving slower than what's observed in the experiments. So people have, in fact, run simulation without collisions of this problem before, and they found the same thing. And they said, well, the reason for this most likely is the fact that we're not fully capturing the velocity fluctuations at the position of the particle. And that we should really say that there's more fluctuation locally because our averaging process and all this and our resolution is such that we can't. You know, people were doing LES and they were saying we don't have the full fluctuations. When I interpolate my fluid velocity to the particle location, I'm underestimating the amount of fluctuation that the fluid imparts to the particle. This was their argument. And this was, in fact, a master thesis from a student from John Eaton, who was doing those things. And so they said, we're going to fix this by modeling the subfilter fluctuations near the wall. And they showed that provided you provide really an enormous amount of subfilter fluctuations, you can indeed flatten this profile. And they concluded, well, we need a better model. We don't have the luxury of doing that. We're doing already a DNS as far as the fluid phase is concerned. We have all the fluctuations that we think exist on this flow. So we didn't really buy into this. Instead, what we thought is, well, if we have this high particle concentration, maybe now collisions are not that negligible anymore. And so we turned on collisions, and that's what we observed. This is the blue curve now. We have much less concentration in the middle, less of a dip in the log low region, and a fairly minimal accumulation near the walls. And directly we saw a flattened profile. So we don't think that this is something that needs to be fixed. At least I would say that me and the colleagues who worked on that, in particular Jesse Capecelatro is now a professor at University of Michigan, were pretty much convinced that this departure from the experiments that people have reported in the past, and they fixed using subgrid fluctuations. It's not a subgrid fluctuation issue. Or let's say it is a lack of fluctuation in the particle phase, but it is due to the fact that the interparticle collisions were not accounted for. That's a good question. I would have to look again. I don't remember it on the top of my head. Probably it is on the order of 5 or 10 or something like this. It is not a negligible Stokes number. Right. Oh, no, I agree with this. No, this is a higher. This is. I think this shows that this is a collisional flow at that scale, even right next to the wall. So, a little bit of an explanation here, kind of wrap up this topic. Why do we see this dip here? Well, that has been known in this field for a while. This is a process that's been named turbophoresis. Okay, this is the action of turbulence leading to preferential concentration. It is a different name for what ends up being very similar to the preferential concentration process of Maxey that we've talked about a few days ago. Vortices, we argue that the appropriate Stokes number would eject particles out. Well, the fact is that turbulence we know will be most intense in the log-low region here. This is where we expect the most intense vorticity. This is where we expect to see the most particles getting ejected out. Okay, so in fact, well, do I have, oh, well, I have it right here. Well, that's good enough. But because that region is the region of most intense turbulence, we end up seeing particles overall being ejected out of that and accumulating in a lower RMS region that corresponds to the center, as well as obviously lower RMS region that corresponds to the very near wall region. This is turbophoresis. Same mechanism on the micro scale as the Maxey-Riley mechanism, but now integrated from the perspective of a wall-bounded turbulent flow. Let's look at the overall dynamics, how are the particles migrating. Okay, so that explains this dip. That also explains why we need collisions. Yes, the overall mass loading is low, but there's an explicit two-way coupling process that leads to particles getting pushed systematically against the wall. So locally, concentration becomes high. Collisions do become important. Okay, so this was a successful validation for dilute two-phase flows. We'll do another two quick engineering type examples for what I'm going to call transitional two-phase flows, regions that are dense, regions that are dilute. First, we're going to go back to the original, well, I don't know if you can really see this, but this is a video of a vertical riser, well, I guess this is a downer flow. We are now going back to modeling a flow like what we were discussing about initially. Vertical tube, particles in this, we're flowing up, particles are raining down, and we're looking at the interaction between these things. The simulation takes a whole lot of time to spin up, but after a while you can see particles are indeed forming dense clusters that rain along the walls. Those clusters, you can identify, track them, and say quantitative things about them from those simulations. There's not a lot of detailed experimental data on this, but there's quite a bit of macroscopic experimental data available that's been used to develop correlations. So we're comparing ourselves to those correlations. One thing here is a correlation proposed by Neumer and Glicksman that reports the relation between the cluster fall velocity, how fast does a cluster go, as a function of the so-called Archimedes number, which you could think of as essentially something like a Reynolds number for a settling particle. Our blue symbols here are our simulations. All the other symbols are from different reactors in labs all over the world. This is the correlation that was provided. I think we're doing okay. I don't know if we're great, but we're at least on the same page. I would argue, so this is now a correlation of the concentration in particles within the cluster. So this is the volume fraction of particles in the cluster based on the overall volume fraction at the location of the cluster. So If you have locally a region of a certain volume fraction, say 10%, how dense should your cluster be? Well, that's something that's been correlated by experimentalists, this data from Harris et al. And those are a number of different simulations from our group. The color symbols are different simulations from our group. The underlying other symbols are from actual risers. So again, I think we match this pretty well. So we think that we can predict clustering and that our simulations contain clustering well. So this is a fun case. This is now liquid. This is water and sand, okay? So this is a sand-water slurry flowing under turbulent condition in a horizontal pipe. You can imagine this is fundamentally a petroleum engineering type of problem. You're looking at essentially tar sand transport in pipelines. The question is, how fast do you need to flow this slurry mixture in order to avoid the formation, the sedimentation of the particles at the bottom and the formation of a static bed? If you have a static bed, bacteria will develop and they will start to corrode the pipeline walls. So you want this to keep flowing, or else you'll have to deal with corrosion. So the question that was given to us was the following. This was from the Shell petroleum company. They came to us, they said, we've tried doing this problem with Fluent, we've tried doing this problem with a number of other codes, we can't get any answer. We have engineering models that predict things all over the place. Can you tell us something concrete about this flow? So we set up this problem. We took, instead of a channel flow, we looked at a pipe flow, we made it horizontal, so we included gravity, and we made it periodic. We distributed particles, put water in it, and made it flow due to a pressure gradient from left to right, and established a steady state. And then what we did is we changed the applied pressure gradient to look at different conditions and see the resuspension in all this. For one case, we were able to compare our concentration in particles as a function of the height in the pipe. So on the left, you have the experimental concentration. Those are 3 ISO levels that they measured. Those are the corresponding 3 ISO levels in concentration that we obtained. And then same thing for the velocity. This particle velocity, streamwise particle velocity. You can see that distribution. There's measurements from the experiments, and those are corresponding measurements. So as far as the mean quantities for the particles, I think we're doing pretty well. The flow that we obtain is complex. It's a highly turbulent flow. So this is now looking at the full velocity. Remember, you've seen this. We're still solving inside now. Even though we have a dense, so here we're looking at, I should say on the left here, we're looking only at the particles. Those are lots and lots of little dots that show every individual particle in our simulation. They're colored by the velocity. White is essentially 0 velocity, and we go up to 0.4 meters per second or so at the very top. So this is a low enough flow that the particles have settled at the bottom. We have a dense bed that is not moving at the bottom, yet we're still solving a flow equation inside. If we were to approximate what's going on in here, we're essentially solving Darcy's equation. Okay? This is now a porous flow model, except we don't have to manually do anything. This is already contained in our equations. At the surface, we see that we're naturally forming dune-type structures, which are known to form naturally when you go through a sediment transport. And then you have a transport layer at the surface, particle bouncing around, et cetera, et cetera. The big question for us is, can we predict the cross-sectional area of the pipe that is blocked by the presence of a static bed as a function of the velocity at which the water is flowing? We had experimental data coming from Norway on this. Those are the black symbols. This is the so-called sand holdup. This is this measure of how much of the pipe is blocked. You can see it's high, getting close to 100% at very low velocities, and as you increase the velocity, this decreases to the point where it's at 0, and it stays at 0 because now all the particles are suspended, everything is moving. This is where you want to operate your pipeline. You don't want to pump any faster than is required, or else you have extra losses, but you don't want to go too far on the left because this is where you'll start to see corrosion. We ran 3 simulations, and you probably cannot see this one, but There's one here where we predicted approximately the right hold-up, same thing here, and then we ran one at a higher liquid velocity where we predicted 0 hold-up. All the particles were moving. We were interested in this critical velocity where we start seeing this hold-up. Well, this was a pain to find experimental in simulation, so we didn't try. What we did is we just extrapolated linearly our 2 calculations here to find our location. You can see that it matches really well with the experimental measurements. So even a flow like this, this is something that we think we can capture pretty well. All right, so that's the end of my first part. I'll just say that we have here presented a pretty comprehensive strategy that we think can do quite a bit. We're using now those type of approaches to do reactive particle-laden flows, for example. We're looking at biomass vapor upgrading in risers and things like that. We think that this is a predictive approach. We also acknowledge, however, that there's still a number of open questions. Wake-wake interactions, particle interactions mediated by the fluid in general, here is a problem. And yet with the Lagrangian approach, we have access to this multi-point data, so we should think about where to take this. How to properly estimate the local unperturbed velocity field is not something that's finished at this point. Any questions on this part? Yes. Mm-hmm. Well, there's the original regime map for this, which I think I included in the course pack, is from El-Ghobashi. He was really the first one to ask the question. Yes. But then there was a follow-up paper where they looked at, you said there's no particle diameter? Yeah. So then, but then there's, I think he included also something with volume fraction. So I think he looked, he had, El-Ghobashi finished, he had some summary paper on this that showed a Stokes number on one axis and a volume fraction on the other axis, talking about particle turbulence modification. So, and I included that at the end of this chapter 4, so what we had yesterday morning. So, and the reference should be there, I think. So that's one of them. There's more, we can talk some more if you want. There's, people have started doing very detailed simulations, typically in QET flows, in simple QET cells, looking at whether we enhance or eliminate turbulence, typically looking at neutrally buoyant particles, to simplify the story a bit, fairly large particles, full particle resolved DNS, okay? And they've started putting together regime maps for that as well. One person who's actively working on this is Eric Clément, C-L-I-M-E-N-T, has been doing those simulations actively. Is at IMFT in Toulouse. C-L-I-M-E-N-T. Okay, and is using Maxi's force coupling methods to make things. But there's other people there. I saw a PhD defense from one of his students recently on that topic, and so that's why I'm mentioning him. So yeah, I'm sure there are more. I'll show you one little exercise in terms of characterizing turbulence modulation, but we're not going to look at fine details of the modulation. We're going to brute force our way through this by changing the mass loading. Okay. Yes? Yes. Yes. Yeah, so we knew this was going to be a problem. And so originally we wanted the simulation to be as short as possible. We were aiming for the so-called minimum pipe unit or minimum channel unit. But we ended up going quite a bit longer. This is, I think, 7 diameters or something like this. I unfortunately don't have so the length here is pretty much as we could afford. This is already about 60 million intercolliding particles. This was an expensive simulation, in particular because it took a long time to develop, and so we couldn't really afford more. The somewhat positive outcome is that you see 4 of those structures. If we were to see only 1, we would say, well, probably it would naturally be much larger, and it's controlled by the size of our domain. If we were to see 2 or 3, same thing. 4, well, it is basically we have a domain long enough to accommodate 4 of those structures, which means that our resolution is about 4 large structures per domain length, which is not enormous, but it is not too bad either, right? Usually you want about an order of magnitude difference. So do we trust the measure of that wavelength? No, it's going to be inaccurate. It's very possible that the correct answer should be 4 point something, right? And yes, the periodic boundary conditions are going to control that, but yeah. So after getting into this, we suddenly I got a bit interested in underwater transport and bed forms and this idea of ridges versus dunes, but there's only one. There's not enough time to look at all those questions. So we think we can predict some of those things, but I haven't pursued that any further. Okay, now what we're going to do is talk about a canonical configuration that we're going to use to understand a bit better two-way coupled flows. So we're going to look at a flow that we've started calling cluster-induced turbulence, CIT. It is an attempt. So this is work done in collaboration with, at the time, Jessica Pestilatro was still my PhD student, and we were working in close collaboration with Rodney Fox. And we have, we've had a shared NSF project for a number of years, and so that's something we've been working on actively. Here's the configuration we're interested in. A box, triply periodic, with gravity. I should have made this gravity vector larger. So there is gravity here, okay? Pointing down, again, as it tends to do. We are distributing particles in this and letting them settle under gravity. Now we have a surrounding fluid that, of course, is going to start getting entrained downwards because of the downward motion of the particles. So this system, if we don't do anything to it, will blow up, right? The particles will fall faster, the fluid will keep getting entrained and fall faster, and this thing will never stop. So what we're going to do is constrain the flow rate of the fluid to be on average 0. So now we're looking at particles settling down due to gravity and fluid that is maintained at 0 velocity overall through global forcing, through essentially a vertical pressure gradient. All right? That doesn't mean that the fluid is not allowed to move. The fluid evolves in any way it wants. It's just going to experience a forcing term that will prevent its mean from evolving away from 0. We let that run. This is what we see. This shows the particle positions on our box. Uniformly distributed originally, so a basic Poisson distribution. As time goes by, you can see that you're forming structures and non-uniform features, and later on, you have those complex features that really give you similar behaviors to what we saw in the Gopalan and Schaefer videos. Dense regions of particles raining down, and very dilute regions in between. And consequence, the flow field is also evolving. It's going from basically being equal to 0 initially to this complex, chaotic, fully three-dimensional velocity field. Why is that? Well, because the particles in dense regions, as they fall, they entrain the fluid. But since we're forcing the fluid to maintain a 0 flow rate overall, that means that the fluid has to rise in regions where particles are not entraining it down. All right? Well, we can do some a priori analysis. The important number here for us is going to be, again, our mass loading. We're going to call it phi. We're going to want it to be larger than 1. The collisions are going to matter. We're going to be looking at some basic non-dimensional characterization of the problem. We can introduce, of course, the characteristic timescale for the particle. We can introduce the terminal velocity of the particle that gives us our velocity scale for the problem. From that, we can define a particle Reynolds number. That particle Reynolds number, we've worked quite a bit with fairly low Reynolds number problems. We have good understanding of the flows at Stokes conditions. We're going to keep that small. The particle Reynolds number will be on the order of 1 and below. Okay, very simple problem, it seems. But we can form another length scale that I'm a bit ahead of time here. I'm going to call it cluster size. This is the distance traveled by a particle as it accelerates from 0 to its terminal velocity. That's a significantly larger length scale. That length scale we can use to generate another Reynolds number that will be now significantly larger. It's going to be a Reynolds number on the order of a few hundreds if that Reynolds number is on the order of 1. Okay? The fact is that in this flow, we find clusters that start emerging, those dense regions that start emerging, on a length scale, and I'll show that corresponds to this distance traveled upon acceleration length scale, L, which means that effectively the Reynolds number that properly characterizes the agitation in this system is indeed this Reynolds number based on L. So it is a turbulent-like flow field, not classical turbulence in any way though, that is entirely caused by the two-phase system. If we did not have the particles, this would not be a turbulent flow. This would remain at this. So this is entirely the clustering dynamics that is creating this turbulence. Okay? 3D chaotic flow at a Reynolds number of a few hundreds coming from the collective dynamics that are emerging from particles moving under Stokes condition. This is fully periodic. We run it till statistically steady state. Now we have a system that's perfect for study. Right? It doesn't vary with time. It doesn't vary with space. So we've been playing with this. We've been analyzing that for a number of years. We varied, for example, the particle Reynolds number, and you can see that this impacts a little bit the cluster size and their characteristics. A few words about the configuration. Typically, we run about on the order of 10 to the 7 to 10 to the 8 particles in a system like that. We account for collisions. Those are pretty large simulations. We're talking about on the order of billion cells. And again, 10 to the 8 cells, or 10 to the 9 cells, and 10 to the 8 particles. So they are big calculations. Why are they this big? Well, because you can see those clusters are large. They encompass a large number of particles. And that's the corresponding flow field. Okay, so once we have something like this, it is important for us to think a little bit about how particles behave to help us analyze this. So we mentioned already the fact that a particle ensemble will have this interesting characteristic that at a given position, particles could coexist that have different velocities. So a full distribution of velocities can exist at a given time, at a given place. That's an interesting feature that makes it different from a classical way of thinking about gas phase flows. So we're going to explicitly take a look at what that means. So this is kind of an example of this. Imagine I have this random field of velocity that has some randomness and some organization. Okay? I'm going to be interested in separating the correlated motion from the uncorrelated motion. The correlated motion would be, I'm going to say it like this instead. Imagine I have all those particles that share the same location, more or less. They have different velocities. I can average that velocity and have an equivalent Eulean velocity for my particle phase. Well, that velocity is going to be my coherent particle velocity. This can still, however, fluctuate. There's still going to be fluctuating energy in that because the flow is turbulent. So that's going to be what we're going to capture here in this Kp. But now, there's going to be lots of different particle velocities around that corresponding Eulean mean particle velocity. The discrepancy between this we'll capture in the form of, in a very classical way, that relates to physical gas dynamics, we're going to capture that in the form of a temperature. So the fact that the particles are kind of bouncing around, even at one location, they're kind of moving in all directions, we're going to say this is because there's a certain temperature. We're just talking about this, we're just naming this a temperature, but this is effectively a granular temperature, and this is just a measure of the random fluctuation in the particle distribution at a given point. Okay, so my point here is that there's two different kinds of fluctuations. There's this local randomness in my velocity, in my particle velocity field, that uncorrelated agitation. That's one element. We're going to call that theta. And then we have, even if you average this out and create a local average particle velocity, that still will fluctuate over space and time because the flow itself is turbulent. So we have particles doing whatever here, but then they'll move down there and do their whatever down there. Okay? This is closer to classical turbulence. This is closer to classical physical gas dynamics. Another way to sketch that also introduces a lot of definitions, but I'm not going to go too much in the details here. Imagine this is a cell. I have my position and particle velocity. All those little dots might be a whole lot of different particles that coexist in this region, but have lots of different realizations of velocities. I can convert that into a mean Eulean velocity for my particle phase. This would be this red line. And we're also going to refer to that as a filtered velocity. This is now the corresponding Eulean information. Now, each position will allow only one velocity to exist. This is inherently what we were doing when we were doing Euler modeling. But then that is still a fluctuating quantity. And so if you want to do Rand's modeling of that, you have to look at how this fluctuates around its true mean. Okay, so there's those two levels that we'll have to think about. That allows us to start thinking about how to process our data. This shows each little dot is a particle in our flow. This is looking from the top, this is looking from the side in our cluster-induced turbulence calculation. Each little dot is a particle. This is colored now by its instantaneous velocity. Okay? I can apply the type of filtering techniques, at least a variant of that, on my particle data and convert that into a Eulean velocity field. Now what we've done is we've gone from many different velocities at a given point to a single average velocity at that point. Okay? This is now a Eulean field. I can measure now the amount of agitation that is in this. I can now compute the amount of if you will, TKE associated with this Eulean velocity, and that looks like this. But in the same way, I can look at the difference between these two and measure the amount of fluctuation that's contained in this, in between these two. And that will give me my granular temperature. So this is an important plot because as far as I know, this is one of the first plots that at least I've seen of this type of concept. This is the granular temperature shown in a pointwise and instantaneous way extracted from a particle field. What am I looking at here? Well, high or red or darker regions are regions of high temperature. And kind of in the same way as in the gas. This is regions where the particles are going in all types of directions. There's a lot of uncorrelated motion. Lighter regions are regions where particles are essentially moving together. Okay? Now, some interesting things here. We can see, and I guess I'll show that. Well, I'll skip one thing quickly here. This is a validation for the process that we use to do this. Let me skip that. Let me show you instead a movie of this. So this is a 2D cut through this process. You can see those clusters raining down. And now on the fly on the right, we're extracting the granular temperature of this particle phase. So some on the fly measure of its heat as measured from the amount of uncorrelated dynamics. You can see here an isosurface. The black line is an isosurface of high volume fraction. So inside there, you have clusters. Outside, very few particles. What are we seeing? Well, we're seeing interesting things like the fact that the granular temperature peaks right below the clusters. Is that a surprise? Well, if we think about compressible flows or re-entry vehicles, not really. This is a rarefied gas flow that is now where we have some dense stuff that's moving rapidly. Well, we're going to form essentially a shock. And what we're seeing here is compressive heating. This is compressive heating of our particle phase. Well, what we also know is that this pushes back on the cluster. So one of the mechanisms by which clusters are finding their terminal velocities is because they're falling into particles that are not moving at their velocity, and those particles hit them, and that slows them down. We can extract lots of statistics from all this. One piece of information that is interesting because it connects a bit to some of what we were talking about earlier this week. Volume fraction is a quantity that can only go from 0 to some high number that shouldn't go above 0.6 or something like that, depending on the polydispersity. It is, if you're running a simulation where your volume fraction is on the order of 1%, it's essentially only bounded by 0. You would expect turbulence to help you, or the randomness of nature to help you form some sort of a log normal distribution there in terms of probability density function of volume fraction. And that's exactly what we find. We start our simulations with a Poisson distribution, right? Random distribution, random uniform distribution. That's where we start our simulation. We let those simulations evolve, and they all systematically, nicely collapse, or not perfectly, but near perfectly collapse on the log normal distribution. Meaning, it is less likely to find particles at our mean initial concentration. It is much more likely to find regions with much fewer particles, but it's also way more likely to find regions that are much denser. Okay? We extend tails on both sides. We have regions empty, devoid of particles, regions with lots of particles. We can compute radial distribution functions. We hinted at that a little bit before. I'm not going to go through the details, but basically we can extract what is the characteristic length scale for those clusters. Those clusters, we find, they tend to be on the order of this L length scale, the distance traveled by a particle as it accelerates from 0 to its terminal velocity. I'll make one quick observation to conclude this part, which is that our Reynolds stresses in the flow, so our fluid Reynolds stresses, which are an important quantity if you want to model this from say a Reynolds average Navier-Stokes standpoint, they are highly anisotropic. This flow exhibits high levels of fluctuations in the vertical direction, very low levels of fluctuations in the diagonal direction, in the off-diagonal directions, as well as in the lateral directions. What does it mean? Well, if you're thinking about modeling a riser or a downer using a K-epsilon type of strategy, I think it's probably hopeless. That's essentially what this teaches us. If you want to do macro scale engineering type of modeling with RENS for a system that involves falling particles, I think Reynolds stresses type of approaches are required. I have some summary statements here, but I think we talked about all of this. Any questions on this? Yes? Yes. Well, we didn't do it. Maybe. I don't know of. So we have for a number of years my group in collaboration with Rodney Fox and very few others have been, I think, the only people looking really at those questions from that very fundamental perspective. There's a lot of people doing full particle resolved direct numerical simulations of similar problems too. And these people provide even more, so they have more trustworthy results, right? Because they're resolving everything. However, they're limited to much smaller systems, and so they are severely constraining the emerging dynamics, right? We're looking at hundreds of millions of particles. So there's been those two ways of approaching this problem, one from the fully resolved standpoint, the pure DNS standpoint, and that's not made it to this type of clustering. And there's been our approach, taking Euler-Lagrange and scaling it up to the point where we can see those emerging dynamics. and I'm not aware of many other studies like that. There are a few, right? Well, you never work in a vacuum, but I don't think I've seen anything at higher Reynolds numbers. There's no enormous challenge. There are some challenges, but no enormous challenge with doing that. So to me, it's an open question. Having said that, in the fluidized bed reactor, you're not going to find enormous Reynolds numbers typically, but in other applications, you might. So, other questions? So, in the interest of, I'll go a little bit quick in the next 2-3 slides because I really want to go to the few slides that, in fact, I've added compared to what. So this is where we probably are departing a bit from what I included in your course pack. Sorry about that. And I'd be happy to provide all the final notes to Dr. Day. We've been talking about all those methods, but we have a set of closed closed equations, provided we've introduced sufficient modeling. We have a set of equations. We can now look at Reynolds averaging them and think about what the resulting model, Rance model, would look like if we wanted to capture this. So we've done that. This has been, so Rodney Fox is an outstanding turbulence modeler, and so this has been a key part of his activity in this project with us. So he's been deriving all those equations, basically applying ensemble averaging, or in this case, in this case is temporally stationary and spatially homogeneous, so we can average that in all directions you want. Everything averages out. In fact, we should be able to write all this in the form of a simple, a Rance model should take the form of a simple algebraic model down the road. But anyway, you can derive those equations and look a little bit at what's going on. Why are those clusters here? What's going on? Well, I'll just highlight a couple of interesting features that the equations are teaching us. In particular, this is the evolution equation for the Reynolds stress in the vertical direction for the fluid. This equation shows that there's one very interesting term here. This term is a production of Reynolds stress, so production of TKE, if you will, in the fluid phase, coming from the drag. Specifically, this is coming from the fact that there is a difference between the mean fluid velocity and the mean fluid velocity as seen by the particles. The particles are not uniformly distributed, therefore they preferentially sample different regions of the flow field, and as a result, we end up with a non-zero production term that ends up generating turbulent kinetic energy. So the agitation in the flow field is created by the clustering. Right? The fact is here that particles are mostly present in dense clusters. Those dense clusters are falling down. They're entraining the fluid with them. Therefore, for the most part, particles sample fluid velocities that are large and negative, and they miss most of the fluid velocity that's positive. So that's how we end up pumping energy into the flow. You can, there's one interesting connection also that shouldn't be surprising, but you know that when you're looking at turbulence, turbulence gets dissipated into heat, right? You have velocity fluctuations, and through the action of viscosity, you dissipate that into heat. Well, this is the same story here. We have correlated agitation in our particle field. There's a sink term that I'm writing right here, which is a turbulent dissipation of that correlated fluctuation in the particle velocity. That shows up as a source term in our granular temperature equation. I'm not, in fact, writing the granular temperature equation here, but the particle phase stress tensor, of which the granular temperature is the trace. So, turbulence in the particle phase, the coherent dynamics in the particle phase leads to dissipation. That dissipation shows up as a source term in the particle granular temperature. So what you dissipate into those from those coherent motions, you get it back into random agitation in the particle phase. And all those equations are exact. You derive that exactly. There's nothing magic here. So that allows us to give kind of a story of this cluster-induced turbulence. Gravity is ultimately what produces the turbulence, produces the slip between the phases. Once you have slip between the phases, and provided your mass loading is not too small, you're going to start pumping energy. Well, first of all, if you didn't have any fluctuations, you create slip, that generates drag. That drag leads to a viscous term that dissipates all this into heat, and you're all done. But if you have fluctuations, any type of fluctuations will pump energy into the fluid decay. Okay, so any non-uniformity in the particle distribution will generate turbulent kinetic energy in the fluid phase, which will in turn agitate the particle phase as well. Okay, and which will in turn feed back into all this. And then all that energy in different routes gets back into heat as well. Ultimately, everything makes it into fluid temperature. Okay. Now, what if I put walls? So we were looking at those big clusters, let alone to develop on large domains. As soon as I put walls, provided those walls are not significantly wider than this capital L cluster lengths that we've defined, well, suddenly the clusters can develop freely, and they're going to be constrained by the presence of the wall. What's going to be happening? Well, those clusters are going to accumulate in the walls where it's favorable for them to be because there is no fluid velocity pushing them up because of the hydrodynamic boundary layers. So you end up in situations like this. This is, particle-laden vertical channel flow at fairly high mass loading. The other way to think about it is this is a cluster-induced turbulence problem to which we've added walls on the side. Okay? But the addition of the walls on the side has forced all our clusters to sit at the walls because they can't develop to their full size. Let's look at one canonical, one specific case study of such a wall-bounded flow. We're going to look again at turbulent channel flow. We're going to reduce the Reynolds number, the RE tau, from the previous one. This was way too expensive. It took us a long time. So instead of doing 600, we're going to go back down to 300 for RE tau. It's still fully turbulent. Our method doesn't really care what our local mesh size is. It absolutely lets us use a mesh size that is less than the particle diameter, right? We've introduced a filter to really free up those two concepts. And so we're going to use a proper boundary layer mesh to fully capture the wall boundary layer in this system. What we're going to do is we're going to put particles in there at different mass loadings. So we're going to put a few particles, more and more and more and more, and we're going to look at what happens, how this turbulent channel flow transitions as we increase the Reynolds number, the mass loading. Okay, so those are some of the parameters. Nothing extremely critical here. You'll notice that we've increased the particle Reynolds number to 10 here. Okay, another potentially interesting piece of information is the Stokes number. Even the friction-based Stokes number, the ST plus, if you will, is 2. The Stokes number in the center of the domain is 20. Those particles are not highly influenced by the fluid, but they know about the fluid. And now we're going to crank up the mass loading from 0, single phase flow, that we can validate, all the way up to 20. So I should have shown that vertically. Again, there is gravity here, but it was easier to organize that horizontally. This is a mass loading of 0.2, so 20% of our mass is in the particles. Down to there, we have 20 times more mass in the particles than in the fluid. You can see the evolution of the flow field. This is essentially very much what you would expect a single-phase turbulent channel flow to look like. And then there's those little dots that correspond to the few particles floating around. You can clearly see this transition from single-phase turbulence to down there, this purely cluster-controlled flow, right? We don't have the same thing at all between the top and the bottom. Seeing that, we saw, so this is major modulation. We're talking about turbulence modulation. People have been looking at tuning turbulence and changing the spectrum a bit. But let's first ask ourselves, what is a mass loading that's sufficient for the particles to control the dynamics? What is a mass loading that's low enough that the particles don't matter for the dynamics? Well, this is essentially a single-phase flow. The turbulence here is controlled by the mean velocity gradient production. This is essentially a wall-bounded CIT case. The production of turbulence comes entirely from this drag production term I showed a couple of slides ago. In between, we're pretty excited to see this. This is not something that we were expecting. When I look at that, I start asking myself whether we've really aminorized the flow. There's almost nothing going on here. So we wanted to quantify that a bit. So we went back to the to the fluid phase turbulent kinetic energy budget. Okay, we wanted to look at where the agitation in the flow was coming from. We're plotting all this on the same scales. This case here is corresponding to this 0.2 case. This is almost a single phase case. Down there it's 20, and this is in between. First of all, we're not going to discuss that in details, but essentially we expect this mean shear production to be the main source of turbulence. This is what we see. And this is balanced essentially by viscous dissipation. That's what we would expect from Steve Pope's textbook on turbulent flows, if you will, or any other place. There's a bit more. We're not going to go into details here. This behaves essentially like a single-phase flow. The particles don't play much of a role in those dynamics. This corresponds to what we studied before with our CIT problem. Those other terms, shear production, viscous dissipation, they don't play a role. The particles entirely control the problem here. Drag is what produces turbulence. Drag is what dissipates turbulence. The fact that groups of particles entrain faster particles in certain regions than other regions, that's what creates our agitation. The fact that the drag term is not energy conserving and it leads to boundary layers at the surface and dissipates energy, that's what leads to dissipation. Okay? So the particles mediate everything here. In between, essentially nothing. At least on that scale, nothing. So we were pretty excited by that. I've been going around universities trying to convince experimentalists to pour the buckets of sands in their experimental apparatus required to go up to this value. I have not yet been able to convince anyone, go figure. But maybe I should go the other way around, talk to chemical engineers who are used to doing that and ask them to put just a little bit less sand. But we'll see. This is something that we're hoping to confirm from experiments. Much simpler way to think about it is a simple friction coefficient, okay, an integral measure of what it takes to get this flow going. Well, we know exactly what it takes to get this flow going if you're at the limit of no mass loading, right? Zero mass loading, no particles. This is I'm forgetting my fluid mechanics. So from Blasius' original PhD work, he had all this correlated. the CF as a function of Reynolds number. We know what it is in the unleavened case, and that's the Blasius correlation is down there. So at our low mass loading, we're pretty much on top of it. We match this. That's expected. We argued that the particles were not doing much. At high mass loading, well, those particles are doing quite a bit. They are also bouncing on the wall. They add a lot of extra dissipation in our system, so we end up with a lot of extra friction. No big surprise that we should shoot up. But what we were very interested in seeing is that this is in fact non-monotonic. We're expecting to go from a low value of from a Blasius value of the friction coefficient to something that increased rapidly with mass loading. What we're seeing is we first dip before going up. So it seems that it is easier to flow a few particles than no particles at all. Okay, that's work in progress. I have some summary here in perspective. I want to say, I guess, in perspective that simple questions like simply mass loading transition in particle-laden flows. I don't know many studies like this. I think this is one study that we're in the process of publishing in JFM, but I don't know of many of studies like that. The simple question of how high of a mass loading do you need to reliminarize a flow? So imagine I remove gravity, okay? No gravity. I just have a turbulent flow and I add particles. How many particles do I need to add in order to fully reliminarize a flow? Am I even going to be able to reliminarize a flow? How will the flow look like? I don't think we know this. So there's a lot of work that remains to be done. I think the simulation approach I showed is very powerful, and you can take that quite a bit further. That's everything I've shown here. I think that suggests that we can certainly use CFD as a discovery tool for particle-laden flows in terms of elucidating the physics. As an engineering tool, well, for dilute flows, we've discussed about a number of things that work well. For high mass loading flows, we've discussed about a number of things that work well as well, but it's more difficult. There's a lot of modeling questions. You find out, a lot of fluidized bed reactors are being designed today using K-epsilon type models. We think it's bogus. I don't think this is something that can be done in a reasonable way. So there's still a lot of work that's required. That's kind of my perspective on this. I have this acknowledgement slide. Really here, a lot of the work came from Jessica Pasilatro, who's now an assistant professor at the University of Michigan. A lot of collaboration with Rodney Fox, and some of the funding is from NSF, some of the funding is from the OE Office of Biomass Research, the RENREL, the Shell Petroleum Corporation, and a few others, and then the supercomputing resources are here. All right. Be happy to take any additional questions if you have, and else, thank you. Mm-hmm. Yeah, so am I interested? I am very interested. It makes a lot of sense to go in this direction. For example, how would we formulate a larger dissimulation version of this cluster-induced turbulence canonical flow problem? So far, what we've done is we've looked at what a Rance model of this would look like, and we've published that. So the Rance version of it would be a single set of coupled equation for the entire box. We don't need a grid for this. The LES, we would need a coarse grid, basically. And we would need a different set of closures. So we haven't started looking at that. We are interested in looking at that. This is definitely the direction in which we're going. We've started crunching some of the data from the perspective of LES. Some people are ahead of us in that direction, and I've started with LES directly and not Rance. And in particular, one person is Sundaresan at Princeton University in chemical engineering there. what they've done, they've tried to develop the LES models that would allow them to get similar data. Using in part our data and using also data that they've recreated for the same case. The underlying assumption when you want to run an LES type of approach is this idea of cascade, of self-similarity, of being able, at least if you want to have some sort of a dynamic modeling approach, you would want to be able to say that your knowledge on the resolve scale is sufficient to close your model at the under resolve scale. I've seen a presentation by Sundarasan, a number of presentations, where he's claiming that he thinks this is a cascade process, that a big cluster is a medium cluster is a small cluster, which then provides, if you believe that, then there's hope. I don't think I believe that. I have doubts, at least. So that's one of the things I'd like to do in the this year is to look at this data and ask exactly that question. Is there some sort of a scale similarity going on here? If I look at those clusters on a large scale, a medium scale, a small scale, do they share similarities in any way? I don't think I see that. I think when I look at it, I see big chunks of stuff. I don't see big things that organize medium things that organize small things. I don't think I see that. But then again, my eyes are not, they're not a proper mathematical post-processing of this. So honestly, my guess is that this is not going to be an easy problem to handle using LES. Something tells me that there's one inherent cluster length scale, and that if your LES is not capable of capturing that length scale, you'll pretty much have to re-inject all the physics of clustering in your model. And if it is capable of capturing that length scale, then you would just have to be able to say something about, you would just need to be a bit careful about you write your LES, but you would have most of the physics. So I think there's decent hope that we can have models that go down to the cluster scale and nothing more. And I think anything larger than that will require more hand-wavy approaches, energy minimization type of approaches like this. A lot of models in the context of RANs for this type of things that exist. So that's kind of my perspective of that. So it's I've started thinking about it, but I don't have data. We haven't really. But yeah, we're interested. So it's a very, very good observation. Other questions? Okay. If not, thank you. Thank you for your patience. So we've essentially merged everything we were supposed to do this afternoon with the past couple of days. So we're done until Monday morning now. Okay. So Monday morning we'll meet up again. I think usual place, usual time, and this time we'll shift our focus. We'll leave our particles behind, and we'll talk about liquid-gas interfaces. Thank you very much, and enjoy your weekend.